I know a lot of my friends and family have been through a lot in the last couple of years, but hopefully the next 2 will see a lot more people getting vaccinated, protecting themselves, and just generally staying safer. But but it's good to see you all here. I'm glad nobody in this lab was horribly affected. Too bad. But today we're going to kind of ease into this year with an interesting thought experiment, thinking of AFMIR and modeling this system as a type of engine where we put in energy and we get out work of some sort. So as a little bit of background, Ernst Abbe first kind of coined the diffraction limit of light. He was actually one of the co-founders of Zeiss, which I'm sure you've all heard of. And his rule essentially states that the smallest resolvable distance between 2 points using a conventional microscope may never be smaller than half of the wavelength of the imaging light. Now, in terms of visible light, the smallest wavelength is about 400 nanometers, so about half of that would be about 200 nanometers. That would be about as small as you could see using a conventional microscope. So in terms of size scale, an ant is around the size scale. Between an ant and a hair, that's about 1 millimeter, down to bacterium or mitochondria, about 1 micron. Of course, the virus itself, or the coronavirus in our case, is about 100 nanometers in diameter across. But as we move down further on the size scale, we get into more interesting features, especially in our case, and that is the size scale of molecules or polymers. And so here's a good example of the limitation of diffraction of light. So in the case of good resolution, where we have this true image, where we have 2 dots spaced about a micron apart, if the wavelength is smaller than the length scale that you're looking at, the true image and what you see should be 1-to-1, should be identical. In the case of poor resolution, where the wavelength is greater than the length scale, it creates this blurry image here. So scientists were looking for ways on bypassing this diffraction limit of light. So here is the visible region. My laser is a little weak today. So people saw the photothermal effect as a way of bypassing this limitation or the diffraction limits of light, because if our target is looking at molecules, then why not take advantage of certain wavelengths of light that excite these molecules? And so people began looking at the photothermal conversion, because if we look in the infrared region, this is the region that begins to create molecular vibrations, and to where we can actually get a response from our materials if we shine them with the correct wavelength. So this is the photothermal effect, and this is how we're going to bypass the diffraction limit of light. Now, I know a lot of you have just gone through this exact same slide probably 24 times already, but I'm sure when I'm gone, somebody will take over for me, so I think it's good to go over this little bit of background. One way people have bypassed the diffraction of light is using AFMIR, which uses this photothermal effect, where we can shine our material, which this can be a material blend, it can be a composite, really any material, but it must be excited with a particular wavelength of light that corresponds to the excitation or resonant frequency of your molecule. So when we shine in a laser, and it's a monochromatic laser, of course, when it absorbs light at that particular wavelength, we create a rapid thermal excitation, which is then detected by this cantilever probe. Now it detects this thermal excitation or expansion in the form of deflection. And so using this technique, we can create an absorption spectrum from these cantilever oscillations, as shown here. And so this will mimic what you might see in a traditional FTIR spectrum. So this has been used extensively to model different morphological systems in terms of solar cell polymer blends, composites, and blends as found in like nylon, polypropylene, and other industries. So, for instance, we've seen AFMIR used, and this is more references from around the 2016 area. Some people looked at self-assembled monolayers of polyethylene glycol on gold, blends of nylon blended with natural rubber. And they're able to really define where each of these particular materials resided. Here we have high-impact polypropylene. That's another polymer blend where they were able to identify a core within this intermediate layer, which is then controlled in this matrix formation here. But overall, people have been so excited by what AFMIR can do that they've kind of neglected some of the main the fundamentals of the technique itself. So this says the rapid and successful applications of AFMIR come at the expense of progress towards understanding the underlying physical processes of the technique. And so I found this paper that attempts to model the thermodynamics of the AFMIR process as far as the thermal expansion, where that heat goes and all that, in the context of a traditional engine where we put in energy and we get out work. So based on this, there's still a strong dependence of the AFMIR signal on the mechanical properties of the tip and sample interactions. So that's one of the downsides of AFMIR is, for instance, in the case of some samples that Sonia gave me, they responded so strongly to the infrared signal that I was literally degrading the sample. So we have to come up with a new technique to measure those. And as I said before, little research has been done on the role of heat transfer processes in signal generation. A good example that I found was this paper by our friends up at Oak Ridge. So some of this work was done in Poland, actually. Sorry, not Poland, the Ukraine, where they created this sandwich layer of materials where they had PMMA lodged up against a layer of epoxy. And they measured the thermal response of the epoxy, and here we have the change in temperature on the y-axis, and this is the x-coordinate that corresponds to the lateral distance c. And on the right-hand side, we have the actual thermal expansion in terms of deflection in picometers, and the x-axis as corresponding to the lateral distance in c. You'll notice that the change in temperature between PMMA and epoxy is quite sharp. Temperature change, but the actual deflection is far more gradual. So this tells us that this process is not very efficient at all. We're losing a great deal of heat. And so if we begin to model this as an engine, which in terms of efficiency many people have done, I wanted to kind of go over, well, what is an engine? The definition of an engine is something that you put in energy to get work out of, as I mentioned before. And so if we model this based on, or try to model the photothermal expansion based on a micromechanical cantilever and compare the cantilever to a piston in a combustion engine, in this case we have 4 different processes. We have the intake, where the air and fuel mixture is pulled in to this chamber here as the piston moves down, as it draws in the air and fuel mixture. You experience compression, where this piston moves up. These valves are closed. And then the spark plug creates a spark, which ignites this air and fuel mixture. And it forces the piston back down, producing work around this rotation as you see here. As the piston moves back up, exhaust moves out through the next valve. And so we can visualize this in a PV diagram, as you can see on the right-hand side, where you receive energy in between process 1 and 2, where we experience max pressure during the compression period. Now, we get an adiabatic expansion when we move from point 2 to point 3, where we get work out, and this is this process here as we're moving the piston downward. From process 3 and 4, we're getting energy out, which is the form of exhaust, and then we're putting energy back into it, and this process completely reverses going from point 4 back up to point 1, moving to a point where we've reached minimum volume once again. So this paper that I found, it states in thermodynamic terms, the measurements, as in an AFMIR experiment, they claim it relies on a microscopic engine. I thought this was an interesting thought experiment. So what they term as an engine is, if we look at the process between 1 and 2, we have a minimum volume, as shown here. As we introduce our light to the system, we see rapid thermal excitation in the process of 2. Moving from 2 to 3, we actually see this thermal expansion occur, and this is where we reach peak volume. From process 3 to 4, we see a loss of temperature and then a decrease in volume back to the first position there. Now, the interesting thing is that normally in a conventional engine, we consider the medium to be gaseous. But in our case in AFMIR, the medium is actually a solid, and that will lead to further implications that I'll discuss later. So this is the basic diagram of the AFMIR itself. You have the probe, you have the excitation light beam. Our working medium is solid, as I said before. But to actually detect the deflection, we have a position monitor here, which a laser is guided onto. We essentially have a laser that's guided onto the head of the cantilever probe, reflected off the probe, and onto the position monitor. And this is how we can detect deflections on the order of picometers. So basically, radiation energy heats a sample. After expanding, delivers the work necessary to deflect the cantilever of the AFM probe. So in this case, we've already seen this diagram where laser is on here, sample delivers work during this expansion process, and we can visualize this on this PV diagram here. Position 1 to 2, max pressure is at the peak temperature here. Max volume is reached when we find in position 3, where we've reached max volume. And at this point, we begin to lose our heat. And so we see this rapid loss of volume, or loss of expansion. And then in this case, the tip actually delivers work to the sample. And we're going to go over 2 different processes in which they model this. Of course, they claim that this system, it can't be 100% efficient. No actual engine has ever achieved 100% efficiency. And so it tends to degrade this PV diagram, or I should mention that the area under this curve is the total amount of work that you're getting from the system, or the integral of this, or the area of this square here. It's not really a square, or rectangle, kind of a curved rectangle. So this is the actual efficiency. So the ideal is the actual solid lines that you see from 1, 2, 3, and 4. But the deflection that we're getting out does not correspond with the actual maximum volume that we're getting from the system. And so it actually turns into a 3-part process instead of a 4-part process, because we're losing the actual movement from 3 and 4, and it's becoming a single point here. So the first case that they go over is a spring-loaded engine with gradual excitation. And this corresponded with many of the older techniques of AFMIR, where they had a laser that was on constantly, and it was essentially chopped at very, very low frequencies. So the material was excited and then, as I said, chopped at lower frequencies. In this case, we are only moving between 2 points, this 1 and 2, from T1 to T2 on this PV diagram. In terms of deflection, we can see how that behaves, just 1, 2, 1, 2, 1, 2 in this zigzag pattern here. Here, where the deflection is equal to the modulus of our tip along with the coefficient of thermal expansion. The change in temperature also correlates with a larger deflection, or a larger max deflection, as well as the area of that change in temperature. And I'll explain what K is later, because that's actually an interesting fact that I found. So in this case, they kind of break down the fundamentals, and I won't spend too long on this slide, but I really wanted to dive deeper on some of these fundamentals, the things that actually affect how we can get a stronger signal in AFMIR. In the case of K, this is the actual cantilever force constant. So this is the force that if you simply placed your probe on the sample, that's the amount of force that the sample experiences from your tip, with no added force. So essentially this means that the stiffer the spring, the less of deflection that we're going to see. So for smaller spring force constants for your spring, which usually corresponds to a softer spring, you're going to become much more sensitive to those changes in deflection, or changes in thermal expansion, I should say. So we can kind of plug in value for area, pi r squared to this area in equation 2. And in terms of equation 3, we can break down r into a combination of the radii of the tip and sample surface, and we can make it a function of this force set point that we automatically set in the instrument. So this will correspond later with a higher deflection limit. And we can break down D. D is a function of Poisson's ratio as well as the Young moduli of the sample and tip. I don't have a term for D, but this is a factor that they inserted into equation 3. So we'll break all this down into a chart later to make it much more digestible. So in the case 2, which is much more correspondent with instruments such as ours, we are actually pulsing the laser at a constant frequency. So in this case, the sample is irradiated with laser pulses of durations ranging from less than a nanosecond to 10 microseconds. So in our case, we're looking at, for our instrument, about 1400 kilohertz. And this induces a rapid deflection of the cantilever, resulting in a ring down pattern. So we essentially treat the laser pulse as a digital signal, which is traced out in this dotted pattern here. But the actual response in the material is quite different, actually. So in this case, on the left-hand side, we're plotting the temperature of the system as a function of time. So if we take this dot to be our, from 1 to 2, the on signal for our laser, the duration of this laser pulse is the pulse width. And then from 3 to 4, laser turns off. And we can see the heat profile of our actual sample, where the sample doesn't heat up exactly how our laser does. We actually see a loss right here, where our sample doesn't reach peak temperature until about zone 3, where we turn off our laser. And so you can see how this might correlate quite strongly with the coefficient of thermal expansion. Because say if your pulse width is too short, your sample will not reach the maximum temperature and eventually the maximum deflection. So I will explain later on why this actually weaves into some of the research that we've done regarding pulse width. And so if we look in this on a PV diagram, we see that we actually can get an efficiency greater than 0. Whereas we put energy in the form of a laser from position 1 and 2, we see a rapid increase in pressure. In this case, we're still putting laser energy in, but we're getting work out of the system. And this work out is the actual work that the thermal expansion is doing on our cantilever. It's pushing upward until it reaches zone 3, where we reach maximum volume, which should be at position 3 on our left-hand diagram. As we move from 3 to 4, where we're reducing volume, we're getting work into the system, and this is an interesting theory that hasn't really been explored all that much. In this paper, they believe that when the material rapidly thermalizes or decreases in volume, the probe is left above the sample in just a few nanoseconds. It's a few nanoseconds behind the sample in terms of lowering the cantilever down. So it has some potential energy at the top. So imagine if my left hand is the sample, my right hand is the probe. It's fully expanded, and then the sample collapses. Well, you have a gap of time between the time that the probe can return to the sample. And so it transfers potential energy and converts that potential energy into kinetic energy. And so now we're doing work on the sample itself. And that's the process that you're seeing from 3 and 4. Of course, we're getting a lot of thermal energy out, which is our Q out there. So with that in mind, I wanted to look at energy transfer in some of these bilayer films, because the more interfaces you have, in some cases, you will have a greater loss of energy. And there are many different ways you can lose energy. Between the interfaces of the material, as we see here, a few weeks back we created some bilayer samples which were stacked vertically, where we created a barrier layer of polystyrene, and then for our target layer, it was a blend of PLA and polystyrene. And the purpose of this was to create a very well-defined structure that we might be able to see underneath this barrier layer. So this is what we actually saw. So, and we could see this pattern up to over 100 nanometers in depth in terms of a barrier layer, which is pretty surprising. So this is kind of the setup that we had in the top hand portion. The red areas are our target material. You see it's blended with our barrier material. And this is our height here. We don't really see much of any features other than these little pits or dots. Focusing the laser on 1764, which is targeting our PLA, which is blended here in the red zone. We can clearly see them appearing here. Changing the pulse width, as I mentioned before, actually affects how deep we can detect this thermal expansion occurring, because we know our laser is going directly through a material. I mean, these are a few hundred nanometers in thickness. Infrared light is going to go right through them. But it's the thermal energy and expansion that we're trying to detect. Now, if we reduce our pulse width, which again is the area, or I should say the width of how long the laser is on, Sure. In terms of this distance here is called your pulse width. So for shorter pulse widths, your sample will not have enough time, will not be irradiated for long enough to actually create the maximum amount of expansion that you need to detect it. And so going back to here, this is exactly what we saw, was that for short pulse widths, we could only detect the top surface. Only detect the top surface. And what you're seeing here at 1452 is just the polystyrene. If we measure it again at 1764 on the far right-hand side at 20 nanoseconds, that short pulse width, again, we just see noise. It's nothing. So this can also be observed in this AFMIR spectra as seen here, where I took AFMIR spectra at various pulse widths. Now I normalized these to 1452, and so you can see when we maximize the pulse width, which is as far as our instrument can go, it's 200 nanoseconds long. As we decrease that, we see a rapid disappearance of our PLA signal. So this kind of highlights that our material at the bottom is simply not being excited efficiently. So we're not able to detect it. Here I've also plotted the AFMIR signal in terms of the ratio of PLA to polystyrene as a function of pulse width, and you can see how that behaves there. So I wanted to kind of go over again. I explained some points about how the potential energy of the cantilever probe, when it's right above your sample before it collapses back down to meet your sample, is transferred into kinetic energy. And this paper kind of modeled that. So if U is our potential energy and T is our kinetic energy, we see from A moving to this part here, we see rapid thermal expansion. The cantilever stays at this height before it must return to before it returns to the actual compressed or thermalized sample until it reaches the lowest volume. So all this energy, all this potential energy is then transferred into kinetic energy, returning work into the sample. So energy in, energy out. So when this material, when this cantilever returns to your sample, you can have three different processes that occurs. Currently, we use the resonant mode, but I'll go over what might happen if, say, your material is quite soft, as in the case of Sonia's sample, I believe, or it behaved as a very soft material in response to the infrared light. I should say that I got similar responses from softer materials as I did with your samples, not necessarily that they're a higher modulus. So for a lightly damp sample, you will see this ring down effect of your deflection as a function of time. For a highly damp material, you're going to see something very different. So for softer materials, you'll see this automatic decrease in inflection and then a flattening. In our case, we're using a resonant mode where we're using the actual frequency of our laser to excite the material that causes our cantilever to resonate at its resonant frequency. And so we never see this ring down at all, but we keep it in its resonant mode. And this actually increases the sensitivity of our instrument overall. So you can see that the overall energy, which is potential energy and kinetic energy, is a function of the mass of the cantilever times the frequency or the resonant frequency of the cantilever times our maximum deflection. So here's the table that I promised you that kind of breaks down everything into a more digestible table. So here's the different parameters and their expected correlation with the AFMIR signal itself. So in terms of the cantilever force constant, which I explained a little bit earlier, we're supposed to see a negative effect on the AFMIR signal. In terms of the tip sample contact surface, we want to maximize that in order to optimize our signal. In terms of young moduli of the probe and sample tip, this one's going to be a little bit challenging to maximize because you can only increase the young moduli of the tip itself until you so much before you actually begin increasing your cantilever force constant, which balances this modulus out. The thermal expansion coefficient of the sample itself, that's going to, of course, maximize the signal that you get in terms of a resonant response. Turns out the Poisson ratio of the tip and sample, it has a negative correlation with the AFMIR signal. Adjusting the force set point will also increase sensitivity, as well as decreasing the radius of the tip itself. That's going to increase your resolution, but may also increase your actual probe sensitivity. And of course, we want to maximize, this is the big one, maximize the change in temperature of our sample. That is probably one of the easiest ones to address, and that's where I think more research is going towards in the future. The reason why I believe that currently is that one school of thought is you lose a great deal of that thermal energy that you put into the material, or you got out of the material. You lose some of that thermal energy through the cantilever probe itself, because it is quite conductive, thermally conductive. And so one group, and this is something that I showed in a previous presentation, but for a different purpose. One group looked at the energy loss, used energy loss spectroscopy to look at the plasmonic effect at the tip itself. And they modeled this. So they found the different areas where you might actually be losing thermal energy during the process. So if we can somehow insulate this process, we can increase the efficiency of our signal detection of our material expansion. There are other potential interactions that will need to be addressed before we fully understand the fundamental aspect of the thermodynamics in AFMIR, such as optical, photoacoustic, electrostatic, and different magnetic effects. But this is just one instrument, but it's a massive massive field. So in summary, AFMIR unlocks new paths towards understanding nanoscale chemical interactions due to its ability to bypass the diffraction limit of light. That's great. The photothermal heat transfer processes in AFMIR are complex and remain poorly understood, unfortunately. But a few people have attempted to model it, some successfully, some unsuccessfully. And lastly, the detection limit of AFMIR photothermal expansion can be modeled based on the assumption that AFMIR measurements rely on this, as I said before, a microscopic engine which converts heat into work. So with that, I'll take any questions. In terms of safety, we have a few variants going around. So I know a lot of people like to wear these cloth masks like I do just for their breathability. Maybe double them up, or if you're going to wear them, turns out silk does a little bit better than traditional cotton. So I know Kundu likes to wear her silk mask, so that's an option. But yeah. Thank y'all.
Question for
Luke?
Yeah, on slide 14, you were showing one of the, temperature this time plots. And you showed that decay going from 1 to 2, and then at 3 it reaches a height. That's also, just a question about that. That should also depend on the functional group you are actually illuminating with the IR, and then the concentration of that in the actual polymer, right?
So it's both. So it's directly correlated to both the thermal coefficient, thermal expansion coefficient, which is a material property, and the actual concentration of that material. So if you look back at Beer's law, it is concentration dependent as well. And that's why if we get very, very thick samples, obviously higher concentration than a thin film, you might actually begin degrading your sample because of the amount of heat that you generate in that sample.
Gotcha. And then kind of branching off of that, I was curious in terms of your table that you had.
Yes.
You were saying the modulus of the film and tip, as that increases, it's positive for your signal, but the force constant of the cantilever is negative as that increases.
Right.
Why?
And so you might see this is a little bit more controversial because Alexander Dazi, who helped invent the invention, he believed that it increased or enhanced the AFMIR signal. And then
Force constant or
the modulus itself.
Okay.
There's another paper by Lahiri that debates that and says it actually decreases the signal.
Okay.
So in this case, they believe the school of thought that this young moduli increases the AFMIR signal, but it's a little bit controversial.
But the young moduli and the force constant are indeed connected, right?
Right, generally, yeah, because if you increase the modulus, sometimes, or I should say traditionally, the higher the force constant.
Yeah, I was just thinking back to your to the dip, right? So
All right.
you have the cantilever up above the sample, and you have that decay in temperature, so you have a rapid decay in thermal expansion. And there's that lag time. Is that you have that as a stiffer cantilever, that lag time is going to be less, so you see that decay. But then I guess it also might bounce more by a little bit at a higher frequency when it hits it. But
Right. The stiffer probe or cantilever, generally the higher the frequency in that case.
One other question real quick.
Yeah.
So when we do it, right, we're doing pulses on it. And
Right.
We're defining the pulse width, like you said. Do we actually have a drop? Or how do we know like there's that lag time between that decay? Or is it's partially decayed and then we're hitting it with another pulse and then it's already coming back up? Or?
That is a result of modeling, and no one has actually been able to confirm that the probe ever falls back to the sample, because that amount of time that it would take, as well as being able to detect that at all, is pretty challenging.
Gotcha. Okay.
So no one is actually able to confirm that.
Cool.
It's just a school of thought. Yunfei?
Yeah, so you use your tip to dip it and then relax with your pulse. During this process, will the material show some plastic deformation? Because if you keep this deformation, and then when you do the next pulse, may have some influence?
Yes and no. I remember Kevin Green gave a talk during his prospectus, and he kind of explained some of this. But in contact mode, you're going to see possibly the maximum amount of deformation of your material. It's more likely to cause sample deformation than tapping mode, where we're tapping at a constant frequency. You can still create some sample deformation if your sample is especially soft. I've experienced that myself with some of my softer samples, like something like a soft polyisobutylene, something like that. So yes and no to answer your question. Hi.
Yeah, can you go to the actual result you showed?
Sure.
Yeah.
Yeah, I know the one that you're talking about.
Yeah.
This guy. Yeah. Mm-hmm.
For the absorption peak at 1452, whether you only have a signal for those longer time, or you have all of them, but only, they all overlapped.
Whether I'm seeing overlap at 1452.
Yeah, for the 1452, I can only see the like dark blue, but I'm not sure for the light blue, like 20 or 40 nanoseconds. Do you observe any absorption peak, or it's all?
So the cyan color doesn't really aid this white very well, but they're all normalized at 1452. So they all show this exact same absorption pattern here.
So all the pulse widths can have, they show the signal, but they overlap.
Right. So what I did here is trying to, because when you reduce pulse width, you're also reducing the amount of energy that you're putting into the system, right? And so if you didn't normalize it, you would see this decay automatically from all. So I needed to normalize this at 1452 to see the effect on just 1762.
Okay. And then does that imply like you always want to use the longer pulse width?
So the deeper you go into your sample, the further you want to if you want to dive deep on your sample, get the maximum response in terms of thermal expansion, you want to use a large pulse width, longer pulse width. In our case, we were actually trying to achieve surface sensitivity. So using this kind of rule of thought, we reduced it down to 20, and these are the results that we saw. We could see that we could still see the polystyrene, but we lost track of the PLA buried underneath.
Okay.
So I saw this and said, wow, this really works with some of the work that we've been doing.
Yeah, so basically for the 1452, you only shows one, but if you have like 200 nanosecond pulse width, they still will be same, right? For the signal.
So in this case, 1764, this is 200 nanoseconds and this is 20 nanoseconds.
Yeah, I know for the 7064, they have quite difference, like when you use the 200 nanosecond and the 20 nanosecond, so that's why you should use the 200 nanosecond. And I'm just for 4052, since you don't observe any difference in the nanosecond, then.
So if we did not treat this data at all and we left it as is, we would still be able to see that same structure at 200 nanoseconds at 1452. We should see that exact same structure. It's just that this is post-treatment, so it's normalized at 1452. So that 1452 would not disappear. Because if you detect it at 20 nanoseconds, you will certainly detect it with 200.
Just a comment. So
Mm-hmm.
you should those as the 1762 or 1764?
1764. I misspoke.
No, but your.
Or did I? Oh, yeah, I did. 1762, 1764. Off by 2. It's a labeling thing. Need to fix that. Gurang.
Yeah, I have a general question.
Sure.
Can the substrate reflect the IR light if shine
It can. It can. Well, hang on. Visible light it can. Visible light it can.
How about your IR light?
So it shouldn't be able to.
Oh, okay.
It should pass directly through it.
Even silicon also.
Silicon, it will not pass. It will not pass through as easily, obviously, as a polymer. I had a chart that showed what IR light can pass through and what it can't, and all that. But I should.
How about reflective light?
So you're going to get some like a radiation effect, but I'll have to get back to you on that. If anybody else has any thought on that, just chime in.
What's a radiation effect?
Radiation effect is in you're creating thermal energy. It's related more to thermal than to actual infrared light itself. But
So vibrational relaxation?
sorry,
Vibrational relaxation?
right.
I think a radiational effect would be the emission of light.
Hmm. In that case, no.
So a non-radiative effect?
No, you shouldn't get any kind of reflectance of infrared light in that case in a polymer.
Yeah, my thought was.
Thanks for that.
You mentioned that the IR light can penetrate several hundreds of nanometers.
Right.
And if light, sunlight shining in the ocean, the top surface is much brighter than the deeper region. But for a thin film, if there is any reflection from the bottom,
Hmm.
maybe it becomes more complicated.
Interesting.
I wouldn't be as interested as reflection. I would be more interested in, does the silicon heat up at all in that locally? It also is going to disperse heat very quick compared to the polymer. So maybe it doesn't matter.
Right.
But I was kind of just thinking, like, is there an additional thermal lag where the silicon is actually heated and it keeps the polymer from, decreasing in thermal expansion?
You're going to see that more often with thicker samples too. Or I should say, you'll see a lot more of that thermal thermal loss.
In the bottom in the polymer than.
Right. So that interface between the silicon and your polymer is going to act as kind of a heat sink as well. So you are going to lose some efficiency in signal generation that way as well. The more interfaces that you have. Yeah.
So is that why bulk samples burned up?
Uh,
Because there's a localization of heat and you increase the laser power to try to compensate and then it was too powerful for the material?
Right, and that's why in some of your samples, like the best results that I got was when I was using less than 1% laser power, which I never have to go that low.
That makes sense then.
So-
There's some kind of a localization effect of the heat can't properly compress and then decompress or expand and expand.
Right. Yeah, anything else?
Yeah, I have one more question.
Sure.
So typically the tips are gold to help localize some of, and I could be saying it wrong, but localize some of that plasmonic effect, right?
Right, that's one of the purposes.
What would happen if you insulated the tip?
Ooh.
That would be one of the things, right? Because when the tip hits the surface and it's hot, well, the tip's so much more thermally conductive that it draws heat away. And that's kind of what you were saying, is that if we get rid of that, it decreases the signal. But how does it balance out with the fact that you typically require the tip be gold?
Right, so you need that, first off, you need it to be reflective. You need it to be reflective in order to actually get your deflection, because you're bouncing a laser off the cantilever and onto your photodiode, which tells you your deflection. So you would have to find a material that's highly insulating and highly reflective, which
But
may be,
real quick, sorry.
yeah.
The cantilever can be reflective, but the tip itself, does that need to be?
No, it does not.
Okay.
You know, like an ultra thin silicone layered tip.
Well, they are silicon.
Oh,
Yeah.
well.
You're one step ahead. But yeah.
Okay, interesting.
So
I'm just
again,
curious, like, if there's a balance between like, oh, we are having gold and it's conductive versus we try to make part of it,
a lot of what I explained here is a lot of modeling in theory. And this is areas that, these are thoughts that could be confirmed later or should be confirmed if we're really going to maximize what we can get out of the AFMIR technique. So, but yeah.
If you look at the plasma effect, the uniformity of it, how does it, let's say, intensity decays from the tip to, a certain distance away?
Right. So this is a slide that I took from another presentation that I had made, where we did kind of discuss some of the plasmonic effects and where that occurs on the actual probe itself. And this group modeled it based on this, I guess you'd call this a pyramidal type shape that a lot of sample probes have.
Yeah.
And so it's maximized at all tip points.
The question is that, is the schematic you show on the left reflect that? If you look at what you show on the left, it's more like the absorption expansion is taking a leading role, right?
Right.
And plasmonic effect was not that crucial.
So it would be interesting to see the factor of sample excitation versus the plasmonic effect, because they obviously go hand in hand, but which one contributes more,
Yeah.
I believe is still a mystery.
That's could
In my
influence
mind.
your depth sensitivity, because if the plasmonic effect decays really rapidly, let's say within 20 nanometer it drops to minimal effect, then are we stopped at resolution, depth sensitivity resolution of 20? Should not say resolution, but probably say how deep we can see.
Right.
Are they tied together, or they're influenced but not totally coupled?
In that case, I know that we have a very limited selection of materials that we can use in terms of coatings for our silicon probes, and gold has become the dominant coating for maximizing the plasmonic effect. So we'll have to find other ways of maximizing that at this point, unless we find new materials that induce that plasmonic effect better than gold. Because there are certain materials that you can't use, like silver.
You don't need to. I think the plasmonic effect is not just coupled with material, it's also coupled with the shape, dimension of the tip.
Right.
So you could, in theory, get different shape of the tips and test at the same measurement condition, see how depth sensitivity varies.
Right. That would be right. That would be very interesting, and you could probably do that based on modeling too.
I think modeling will tell. I guess my question or confusion is, which plays a bigger role? What you claim here is you just need to absorb it directly by the laser. But to my understanding, the direct laser emitted by your instrument is not that strong. You have to be coupled or intensified by the tip to create that plasmonic effect, to amplify that amount of heat.
Right. I would argue that the actual thermal expansion is far more important.
Yeah.
Not you can't do it alone, of course, but it plays a much larger role, say 70 or 80%. And I'm just pulling those numbers out of thin air, but I believe it plays a dominant role in actual AFMIR signal generation.
So in that scenario, if you use a regular silicon tip, will you be able to resolve any contrast at all? If it's thermal expansion, you should be able to see it.
Right. Right.
Then will you be able to see, measure it, perform AFMIR?
Yes, because they did this without gold-plated, gold-covered tips in the past. That wasn't necessary. It was only more recently where we began using gold-covered tips to maximize that plasmonic effect. So it obviously helps, but it doesn't play the large role as compared to thermal expansion.
Yeah, that would be useful to confirm.
Right.
The other thing I think, I just feel your story is trying to tell people you can measure berry structure, right? So I would think then to better conveying your story, you should try to make your top surface as smooth as possible. I was surprised that they were so much void dense in the PS covered film, and why is that?
Right. That was some older data when we were using, I believe it was not DIO, it escapes me. What's the name of the material that we coat our silicon wafers on before lifting off?
The PSS.
It was the bad PSS, the salt, the PSS with salt in it. Those created the voids. We identified that early on.
Yeah, if we could replace those data with the newer data, I think your story would be more impactful.
Right.
Because people won't be distracted by those non-essential information.
Sure.
Stupid voids.
I know a lot of people had those issues, yeah.
The salt.
All right. But yeah.
Any other questions, suggestions?
That was fun.
Thank you. I appreciate the questions.
I would suggest that others try to get a balanced introduction versus your data. I think this example is a little bit too heavy in the introduction. I would have preferred to strike a relatively better balance.
Better balance between like background and data.
Yeah, for a better discussion. I mean, what we're talking about is basically that one slides for now.
Mm-hmm.
Okay, for the future one, not just for you, for others. Okay, sounds good.
Sure.
All right, thanks, Nathan.
Yeah. Thank you all. All right. Oh, Sean. Sean, did you have anything?